In the movie Contact, Dr. Ellie Arroway is a radio astronomer who listens to radio emissions from space, hoping to find evidence of alien civilizations. She eventually discovers a radio signal repeating a sequence of prime numbers sent from the Vega star system, an undisputed message from advanced extraterrestrials. However, to the horror of Arroway's team, they also discover something else embedded in the signal, a video feed of Hitler's opening address at the 1936 Summer Olympics in Berlin. So how realistic is a situation like this? Where does science stand on making contact with aliens? Greetings, Earthlings. Welcome to Science Fictionally True. I'm your host, Jimmy. On this channel, we talk about the science, technology, and history behind science fiction topics. We also discuss current events about aspects of our society that are moving from science fiction to science fact. This is the 4th episode in our Fermi Paradox series. Links to previous episodes are in the video description below. In this episode, we'll discuss another class of Fermi Paradox resolutions. The possibility that aliens do exist, but we haven't detected signs of them yet. As we explored in the previous episode, most scientists believe the reason why Earth hasn't been visited by aliens is the vast interstellar distances they need to travel to get here. But that doesn't explain why we haven't heard from any of them. Let's assume that an extraterrestrial civilization discovers interstellar travel is indeed impossible. Well, they may still want to broadcast their existence. Why? They may want to trade knowledge, spread their ideas and religions, or try to just end their cosmic loneliness. So, why haven't we heard from anyone? Let's begin by first surveying the mediums of communication known to science. Then, we can try to deduce what alien civilizations may be using and see if we can detect signs of the communication here on Earth. Electromagnetic radiation is the most common medium of communication used on Earth. The visible light that makes up all the colors you see around us is one specific form of electromagnetic radiation. In physics, electromagnetic radiation is modeled as synchronized oscillations of electric and magnetic fields. Together, they form a propagating electromagnetic wave. The wavelength, or distance between peaks of the wave, determines where on the electromagnetic spectrum it falls. The visible light that our eyes can detect only make up a small portion of the electromagnetic spectrum, ranging from red at about 700 nanometers wavelength to violet at about 400 nanometers wavelength. We get infrared, microwave, and radio waves if we increase the wavelength, and we get ultraviolet, X-rays, and gamma rays if we decrease the wavelength. Regardless of wavelength, all electromagnetic radiation propagates through outer space at the fastest possible speed known to science, the speed of light. In fact, astronomy is simply the science of detecting and interpreting electromagnetic signals from space. We have optical and radio telescopes here on Earth, and we've sent infrared, ultraviolet, X-ray, and gamma ray telescopes into orbit. For these reasons, electromagnetic radiation can be used as a method to communicate over interstellar distances. Alien civilizations can build electromagnetic transmitters, embed their signals with information, then broadcast it to their interstellar neighbors. Another proposed method of interstellar communication is particle signals. Subatomic particles, such as electrons, protons, and atomic nuclei, can travel interstellar distances. In fact, in cosmic ray astronomy, astronomers detect and interpret these particle signals from natural astronomical sources. So, aliens can theoretically encode a message into a particle beam and broadcast it to their interstellar neighbors. But would they do it? Probably not. Outer space is littered with magnetic fields that can distort the trajectory of signals consisting of charged particles, like electrons and protons. This makes communication very risky because there's a high chance the signal won't make it to the intended recipient. But what about non-charged particles? Neutrinos are very low-mass subatomic particles that are electrically neutral. They are created from stellar nuclear reactions and high-energy astrophysical phenomena. Because neutrinos are electrically neutral, their trajectories won't be distorted by magnetic fields. Furthermore, they don't interact much with their environment. This allows them to easily traverse interstellar distances unimpeded. So, should we look for neutrino signals from our interstellar neighbors? Again, probably not. The neutrinos' lack of interaction is also their downfall. They are notoriously difficult to detect. For example, IceCube, a neutrino observatory in the Antarctic, has an area of approximately 1 square kilometer and is 1,000 meters deep, with the top of the detector array buried in the ice at a depth of about 1,500 meters. The observatory cost about $279 million to build. But with all that spending, the IceCube Observatory detects only about 275 neutrinos per day. To give you a sense of how little that is, about 100 trillion neutrinos passes through your body per second. Because detection is so difficult, it's hard to justify using neutrinos to communicate, especially when cheaper and effective alternatives like electromagnetic radiation are available. Gravitational waves are the last communication method we'll go over. Gravitational waves are ripples in space-time created by massive accelerating objects. We know that gravitational waves can travel over interstellar distances. They also travel at the speed of light, the fastest allowable speed in the universe. So, are they a good way of communicating? No, because of their trade-offs. Gravity is a much weaker force than electromagnetism. In order to build a useful gravitational wave transmitter, you first need a massive object, at least as massive as a star. Then, you need to shake the object violently to create ripples in spacetime detectable over interstellar distances. Gravitational waves are also notoriously difficult to detect. Their existence was just first confirmed in 2015 at the Laser Interferometer Gravitational Wave Observatories, or LIGO. 1.3 billion years ago, two black holes merged in a galaxy far away. As they violently spiraled into each other, they generated gravitational waves that emanated throughout our universe. When the waves finally passed through Earth, they stretched and squeezed space in such a way that two light beams traveling in two perpendicular pipes at LIGO went slightly out of step. The wiggles caused by gravitational waves are extremely subtle, so we had to detect them over large distances. The aforementioned pipes used for detection are the LIGO interferometer's arms and are each about 4 kilometers long. And even with arms this long, gravitational waves vary the arms at most by 10 to the negative 18 meters, about 1/10,000th the width of a proton. At the time this video was created, the detection of these gravitational waves is the tiniest measurement ever made. The measurement claimed the 2017 Nobel Prize in Physics, just to give you an idea of the scientific and technical hurdles we had to overcome. As with neutrinos, it's hard to justify using gravitational waves to communicate, especially when cheaper alternatives like electromagnetic radiation are available. We've explored several communication methods, and electromagnetic radiation appears to be the best choice, at least with our current understanding of science. So let's continue our discussion, assuming alien civilizations that want to be heard will be using electromagnetic signals. There are still many questions we'll need to answer, like what frequency we should listen at. Physicists Philip Morrison and Giuseppe Cocconi were the first to investigate this question in the late 1950s. Recall, the wavelength is an important characteristic of an electromagnetic signal. It is inversely proportional to the frequency, which indicate how many periods of the wave fit into 1 second. The wavelength, or frequency, determines which part of the electromagnetic spectrum the radiation belongs in. Morrison and Cocconi reasoned visible light was out of the question because competing starlight would drown out visible light signals. Please keep in mind, laser technology was just in its infancy at the time. They also eliminated X-rays and gamma rays because X-rays and gamma ray telescopes were not available yet. Radio waves seemed to be the obvious and really the only choice. However, radio encompasses a wide range of frequencies, 1 MHz to 300 GHz. At the time, we didn't have the resources required to scan such a large range of frequencies, so where should we narrow our focus? Well, Morrison and Cocconi reasoned that Earth's atmosphere is quietest in that it had the least background noise for frequencies between 1 GHz and 10 GHz, making this the range we could feasibly tune into with detectors on Earth. This range contains some interesting frequencies. Firstly, hydrogen emits electromagnetic radiation strongly at 1.42 GHz. Hydrogen is by far the most abundant element in our universe. Astronomers from advanced extraterrestrial civilizations would have studied it extensively. If alien astronomers wanted to send Earth astronomers a signal, then they might deduce that we studied it extensively too. Therefore, sending and listening to signals at this frequency seemed like a good idea. But wait, there's more. Hydroxyl strongly emits at 1.64 GHz. Hydrogen and hydroxyl combine to form water, which is essential to life as we know it. If broadcasting extraterrestrials also evolved with liquid water, they'd find the hydroxyl frequency significant too. For these reasons, many practicing scientists have argued that aliens would logically broadcast their signal between 1.42 GHz to 1.64 GHz. This frequency is poetically known as the water hole, a play on words that represents something many different animal species on Earth congregate to. But how would we distinguish an artificial radio signal broadcasted by aliens from radio emission due to natural astronomical phenomena? Well, to do that, we need to pay attention to the signal's bandwidth. Bandwidth is the difference between the upper and lower frequencies in a continuous band of frequencies. Electromagnetic radiation from natural phenomena tend to be wideband or have a large bandwidth. Therefore, if alien astronomers want to construct a signal that stands out as artificial, they would want to send the opposite, a narrowband signal, or a signal with a small bandwidth. Interstellar masers emit radiation with bandwidths as low as 300 Hz, the lowest from all known natural phenomena. On the other hand, signals with bandwidths less than 0.1 Hz are easily dispersed by interstellar electron clouds. So, advanced aliens probably wouldn't broadcast at bandwidths lower than that. Therefore, these aforementioned frequencies give us an upper and lower bound on the bandwidths we should be looking for. The search for extraterrestrial intelligence, or SETI, began over 60 years ago when radio astronomers began devoting radio telescope time to scanning the heavens for such artificial electromagnetic signals. So, after 60 years of searching, have they found any signals that were definitively broadcasted by aliens? Unfortunately, no, but there have been a few interesting cases. Astronomer Frank Drake, someone we discussed in episode 1 of this series, was the first to ever conduct a SETI experiment in 1960 at the National Radio Astronomy Observatory. His work was known as Project Ozma. Drake tuned in to 1.42 GHz, the hydrogen frequency, and examined the stars Tau Ceti and Epsilon Eridani, which are about 12 light-years and 10.5 light-years away from our sun respectively. Both stars were sun-like and were reasonably believed to contain habitable planets. Within hours of Project Ozma's commencement, Drake found an artificial signal. However, further investigation revealed it was a false alarm. Drake accidentally eavesdropped on a secret military experiment. Although Drake didn't discover aliens, Project Ozma was significant because it dawned the era of SETI. A second notable case is the WOW signal, detected by astronomer Gary Emin at Ohio State University's Big Ear Radio Telescope in 1977. When reviewing the telescope's recorded data, back then astronomers needed to manually review computer printouts. Emin was so impressed by the result that he circled the printout's reading of the signal's intensity and annotated WOW. Hence, the signal became popularly known as the WOW signal. The WOW signal was a powerful narrowband spike at about 1.45 GHz, lasted a full 72 seconds, and emanated from the constellation Sagittarius. The Big Ear telescopes later tried to relocate the signal in that part of the sky several times but failed. To this day, the origins of the signal remain a mystery. Many regard the WOW signal as the strongest candidate for an alien radio signal ever detected. The last notable case we'll cover in this video is BLC-1. To date, the most comprehensive SETI project is the Breakthrough Listen project. Breakthrough Listen started in 2016 and is privately funded by tech entrepreneur and billionaire Yuri Milner. In April and May of 2019, the project's scientists found an anomalous signal using the Parkes Observatory in Australia. The signal was named BLC1, which stands for Breakthrough Listen Candidate 1. BLC1 was a 982 MHz narrowband signal that seemed to be emanating from Proxima Centauri, the closest star to Earth. And in October 2021, SETI scientists, led by astrophysicist Sophia Sheikh, released their official analysis of the BLC1 signal. Unfortunately, it turns out BLC1 was not coming from Proxima Centauri at all. Instead, it was man-made radio frequency interference, similar to many other signals emanating from Earth the team managed to detect. So it looks like the world will have to continue waiting for a definitive alien radio signal. All these interesting candidate signals, but still nothing definitive. If advanced extraterrestrial civilizations are truly out there, what if the reason we haven't detected anything is because no civilization lives long enough to broadcast their existence? That is, the longevity term in the Drake equation, L, is extremely small, and that makes the number of communicating alien civilizations extremely small as well. They could be destroyed by natural causes such as asteroid impacts, gamma ray bursts, or supervolcanoes. On the other hand, their destruction can also be self-inflicted, as in the case of catastrophic climate change or nuclear winter brought about by overuse of their nuclear arsenal. These apocalypse scenarios are existential threats scientists are actually concerned with, so it's feasible aliens can be wiped out by them as well. We will have a separate series dedicated to realistic apocalypse scenarios in the future, so please tune in when it's available. And that concludes this episode. Why do you think we haven't detected any signals from other extraterrestrial civilizations yet? Please share your thoughts in the comments below. So far, throughout our Fermi Paradox series, we assumed aliens do exist, but for whatever reason, we just haven't been able to confirm their existence. However, what if we've actually been wasting our time looking for them? Please tune in to the next episode where we conclude our 5-part Fermi Paradox series by discussing the last class of Fermi Paradox resolutions, the possibility that aliens do not exist, and the reasons why that may be the case. Again, the reasons covered are based on scientific discoveries or were proposed by practicing scientists. If there are any topics covered in this episode that you'd like to explore further on your own, sources are given in the video description below. If you enjoyed this video, don't forget to hit the like button. Please subscribe to my channel and hit the bell to turn on notifications so you'll be updated when new videos are posted. Also, please let me know in the comments if there are any topics you'd like me to cover in future videos. See y'all next time.